Hey everyone, on behalf of Forge College, welcome to another explainer. Today, we are jumping right into our lesson, integrating permits into client transaction flows and gasless UX. Now, if you've been following along in our overarching track, from EVM to SVM, transitioning from Ethereum to Solana, and specifically diving into advanced ERC patterns like account abstraction, vaults, and permits, you'll remember our last session. In implementing permit structures and signature verification on Solana, we successfully built an incredibly robust on-chain verifier engine. It consumes an off-chain signature, validates the owner, and strictly manages a nonce account. It's a beautiful piece of engineering. But let's be honest, an engine sitting on a workbench, no matter how perfectly tuned, is kind of useless if you don't drop it into a car, right? So today, that is exactly what we're doing. We're going to wire that verifier into a real-world front-end flow to deliver a seamless, gasless experience for your users. Let's get to work. Okay, so here's our engineering blueprint for the day. We'll start with entering the client flow, then move to assembling the transaction envelope, building the TypeScript demo, validation and replay protection, optimizing for gasless UX, and finally, looking ahead at security hardening. All right, part 1. Enter the client flow, bridging off-chain signatures to on-chain execution. So, having that smart contract verifier we built previously is a huge milestone. But it doesn't mean much until we build a bridge between a user clicking approve in their wallet off-chain and the state actually changing on-chain. And the foundation of that bridge? The relayer. You know, I always say the relayer is the absolute unsung hero of Web3. Think about traditional e-commerce for a second. You would never ask a customer to pay a 2-cent database fee just to add an item to their shopping cart. They'd close the tab immediately. In Web3, the relayer is the entity footing the network bill, the gas fee, so your users don't abandon their cards over a fraction of a cent. The relayer takes the user's free off-chain signature, packages it up, pays the Solana network fee, and actually delivers that smooth, gasless UX we're always chasing. Moving on to part 2, assembling the transaction envelope, the anatomy of a permit-backed transaction. Let's start drafting up the architecture here. To make this relayer magic happen, we can't just toss a signature into the void and hope for the best. We have to carefully construct a transaction envelope, which is basically a highly precise set of instructions for the blockchain. We bundle 2 specific steps. Step 1 is the verifier instruction. This is what consumes the user's signature and bumps the nonce to prevent replays. Step 2 is the state-changing instruction, the actual transfer or action the user wants to execute. And why bundle them together like this? One word: atomicity. It guarantees that both of these steps succeed together or they fail together. If the signature is invalid, the whole thing safely rolls back and nothing moves. Which brings us to the absolute golden rule of this blueprint. Ordering matters. Verifier first, then state change. Seriously, if you mess up this order, if you try to execute the state change first and the verifier second, you are essentially handing the keys to the vault to a stranger, letting them grab the cash, and only checking their ID as they're driving away. It defeats the entire purpose. Always, always put the verifier first. That brings us to section 3, building the TypeScript demo, prototyping our gasless engine. All right, enough theory. Let's put some ink to paper and start prototyping using Solana Web3.js. Now, for this phase, an AI-assisted workflow is a real game changer. If you've spent hours wrangling standard prompt responses, you know it can be a headache. But if you give the AI strict engineering-level constraints, like demanding a TypeScript scaffold using Web3.js, split into 2 specific files with explicit nonce handling, it is incredibly fast. Step 1, you scaffold the files. Step 2, run it against a local validator or devnet and watch those logs. And step 3, iterate. Ask for small diffs to optimize your data packing instead of rewriting the whole file from scratch. And notice this clear division of labor right here. We split this into 2 files to mimic a true production setup. Your permit client.ts is your front end. It handles the highly sensitive stuff, taking the owner's key pair and generating the signature, but it never touches a network fee. On the flip side, relayer send.ts is your backend or relayer service. It grabs that signature, does the heavy lifting of assembling the transaction envelope, and submits it while paying the fee. It's a perfectly clean separation of concerns. Let's jump to section 4, validation and replay protection, the stress test. So we've got the engine running. Awesome. But now we have to stress test it. Replay attacks are literally one of the most common threat vectors in Web3, so we absolutely must ensure our engine doesn't execute the same transaction twice. When you're testing this, you need to open your console and verify these 3 specific correctness checks in your on-chain logs. First, did the verifier emit a log confirming the signature was accepted? Second, was the nonce count bumped by exactly 1? Like if it was 41, it has to be 42, no exceptions. And third, check your atomicity. Throw a garbage signature at it and make sure it fails safely without changing any state whatsoever. To really visualize this, imagine a chaotic network scenario. What if two greedy relayers try to submit the exact same signed permit at the exact same millisecond to claim a fee? Well, think of the nonce lifecycle as the ultimate unforgiving bouncer at a club. The bouncer has a very strict list. Transaction A shows up with nonce 41. The bouncer lets it in and immediately crosses 41 off the list, updating it to 42. A millisecond later, transaction B shows up trying to use nonce 41. The bouncer just says, nope, you're not on the list, and bounces it. Only one succeeds, the rest fail. Period. Section 5. Optimizing for gasless UX, polishing the gears. Okay, we have a working, secure engine. But a secure engine that is slow is still going to give you a terrible UX. We want fast. We want optimized. So I need you to burn this number into your brain. 1,200. 1,200 bytes is generally your safe threshold for a single instruction submission on standard network transports. The moment your transaction size starts creeping over 1,200 bytes, you're looking at dropped transactions, high latency, and totally frustrated users. You have to keep it lean. So how exactly do we stay under that limit? It all boils down to serialization. You've got a couple of choices. JSON serialization is super beginner-friendly. It's easy to read in the logs and simple to map. But it is bulky. It takes up a ton of space. Then you have BORSH, or binary serialization. This is the highly optimized lean and mean approach. It shrinks your transaction size significantly, keeping you safely under that 1,200 byte line, though you will have to do a little extra work to update your verifier to decode it. When you look at how these trade-offs map out, it's pretty clear. If you just do a single permit per transaction, your size is small, latency is low, and life is easy. But what if you want to batch multiple permits so the user only clicks approve once for 5 different actions? Suddenly, your payload size balloons and your latency spikes. This is exactly why going with binary BORSH serialization is basically your secret weapon. It keeps the footprint so small that you gain the headroom to batch multiple instructions without breaking the network limits. It's all about picking the right tool for the job. Finally, Section 6, Next Steps, Security Hardening, Preparing for Adversarial Attacks. We've built an incredible blueprint today, but I have to leave you with a bit of a warning. Just because your client flow is working beautifully on a friendly devnet does absolutely not mean it is safe in the dark forest of mainnet. So I want to leave you with this question. Your flow is fast, and it's gasless, but can it survive an adversarial fuzzer? What actually happens when a malicious actor throws millions of corrupted signatures and race conditions at your perfectly ordered code? Well, in our next explainer, we are going to dive deep into security testing, subjecting everything we just built to brutal adversarial attacks. Until then, make sure to visit forge.college to grab the code snippets, review the diagrams, and continue your Web3 journey. Thanks for hanging out with me today, and I'll catch you in the next one.